Probably during this session, and you probably noticed the previous one, a lot of drilling noises going on upstairs. You may have heard me mention earlier, my wife and I, we refer to the upstairs apartment as the divorce apartment, because in the 2.5 years we've been here in this apartment, we've seen 3 couples occupy the upstairs apartment, and the previous 2 got divorced. So we heard all the divorce arguments, just the anger and hatred and passion, so virulent. There's no way that those 2 relationships could survive. So they separated. But as each new couple comes in, they change everything, and they drill and they fix things up the way they want, and makes a lot of noise. So unavoidable, I'm afraid. Okay, so here was saying verbally, finishing off the proof, the only if part, the P only if Q part of the if and only if proof, corollary 3.15. Okay, and then I've used the end of proof marker, the open square, rectangle. Most authors nowadays tend to use square, just an open square. Well, it looks a bit like a rectangle, but usually it's an open square. All right, next major new topic. Well, this section, if you remember, is on variance, variations, modifications to the standard model, if you like, of the Turing machine. And we've been doing we've pretty well finished the multi-tape variation, or variant, A-N-T, of the Turing machine. And now we'll do a second major one. That's the non-deterministic variant of the Turing machine. And the main idea here, and in fact it'll be a theorem starting in this session. In fact, we'll start a theorem on proving. It's a theorem, so of course there's proof that a deterministic Turing machine. Well, put it this way: for each non-deterministic Turing machine, you can construct an equivalent deterministic Turing machine. Let me see if it's worded that way. Every non-deterministic Turing machine has an equivalent deterministic Turing machine. Yeah, so it is. Okay? So if you're given a non-deterministic Turing machine, you can always construct an equivalent. In other words, behaves the same way, has the same power, recognizes the same class of languages as the non-deterministic variant. Okay? That's the main idea. All right. So what is a non-deterministic Turing machine? Now, non-deterministic Turing machine. That's a bit of a mouthful. That's 10 syllables. So Sipser doesn't, but I will. So I'll just use NTM. Okay. And it's just easier. 3 syllables. So NTM, obviously a non-deterministic Turing machine. Right? So we need to explain what is an NTM. How does it work? Well, if you're forgetting what non-determinism is, then go back to chapter 1, section 2. So go to 1.2. It's on page 47 of your textbook. Let me just check if that's correct. 47 of the text. Yeah, non-determinism. 1.2, the section. Okay, so refresh yourself. Now, I can do it a little now. Go back to when we were talking about finite automata, FAs. And, a finite automata, pretty simple. The transition function, all it delivered was the next state. That was it, right? So your transition function is pretty simple. So you, as input, your ordered pair to the transition function would be, as usual, the current state the symbol that you're reading. In this case, it'd be the input symbol in the input string, and the output is just the next state. Okay, so in that context, a non-determinism just meant you had more than one next state, right? When you only have one next state, well, then the next what you do next is determined, right? It's specified. There's only one next state. So in the context of finite automata, non-determinism simply meant there's more than one next state. That was it. That's all, right? And so when that happened, you then got a split. Like if you have you may remember a diagram in chapter 1. If you have a deterministic finite automaton, a DFA, then the history, if you like, you just went from one node to the next, where each node represents a description of the current situation of your finite automaton. You know, what its state is, and what's the current string symbol input. What is that? Now, when you have non-determinism, you get a split. So you get a branching. So if say the next state, and for an NFA, say there are two possible next states. Well, then you get a split. So instead of just having a linear from node to node to node, just one node to the next, you get a split. You can have and then you have two child nodes from the one parent node, and you can have that thing going on many times. So you get a tree. You get a kind of computational tree, and at each time the non-determinism pops up, in other words, you have more than one state, you get a splitting, and then you have, well, say you get a two-way splitting, so two children, two nodes from one parent node. Then you make a copy, in a sense, of the machine, and one takes as its current state, or the new state, one of that is, and the other copy of the machine takes the other new state, and then they independently just continue on doing their processing. Well, you have something similar with a non-deterministic Turing machine, but this time the non-determinism is not restricted to only more than one state. Okay. In fact, the state you could have the state could change. You could have more than one state. You could have more than one next symbol that you write with the header, and you could have more than one possibility for the move. You know, like you could have it moving left, or you could have it moving right, something like that. Okay, so there are more possibilities for non-determinism, more choices, if you like, right? Whereas with the finite automaton, there was only the right-hand side here with your transition function was only Q. That was it. So non-determinism then had to be, well, there's more than one next state. But here, you've got a triple product, a Cartesian product of three sets. So you can get non-determinism with the state changing, with the symbol to be written could change. I mean, not change. Could be more than one of them. So you could have more than one possible symbol gets written, or it's all combinations, and you can have more than one possible move. You could have left or right, or all three of them, left or right. Oh, here